Hi there, I'm Mike Glass with Orion Technical Solutions, and today I'm going to discuss a question that I posed on social media in reference to instrument damping. Okay, so the question is as follows. Which of the following is most correct situation to configure 30 seconds of damping in a level safety transmitter described below? The assumptions for this question are that it's a magnetostrictive type level transmitter. It's being used as a safety shutdown device. The transmitter has a 4 to 20 milliamp output, feeding a high trip and a low trip for a horizontal vessel on a floating marine platform, ship, whatever. And the answers are shown below here: A, B, C, and D. A is when the indicated levels are fluctuating severely due to liquid sloshing in the vessel because of heavy seas, such as a marine vessel or a floating oil platform. Option B is when the magnetostrictive level transmitter is experiencing high vibrations, which causes problems with those. It's producing short, high-level spikes that could potentially cause a shutdown. Option C is when the normal fill rate for the vessel is slower than 25% per minute. And option D is that none of the above are correct, and you'd have to explain that answer. Okay, so here's the answers and explanations. Answer A is wrong. To understand why, we got to review what damping is and how it works. Damping is a natural phenomenon. Most natural measurements, almost any physical action, in fact, that are being acted upon by an outside source. Anytime a change is self-limited, it will exhibit this basic characteristic. In engineering and physics, this is referred to as a first-order filter. Damping tends to smooth out noisy signals. Contrary to common misconceptions about damping, instrument damping doesn't work like averaging at all, and it is definitely not a pure time delay, which is one of the most common gross misconceptions. We'll look at the graph on the following slide to explain that a bit more. Okay, so the trend below shows the impact of various amounts of damping or filtering during a normal bump test, during a manual bump test, and it shows the response of each. In this scenario, the bump test, we're pretending that we took manual control of an output and we had it at 40% and we entered 50% and observed the change, assuming the plant conditions are such that you can do this test. That's normally how we determine all this to set damping. So the blue line, if you can look through all the noise, you can see that blue line was the bump change. And that's a characteristic response of a lot of process control systems that are self-limiting. They'll come up and they'll gradually rise like that. So that blue line is very smooth. There's no noise there. That's the ideal. That's the real thing without noise. The red line shows typical process noise on that signal, which is what you're often going to see if you don't have any damping. You may see this could be a temperature fluctuations due to the fact that not all the water that goes through a heat exchanger gets equally heated. There's cold spots, warm spots, etc. And it causes small variations in the temperature reading. And the same thing could happen to a lot of process variables. The green line shows a well filtered or properly dampened signal, or a more dampened signal at least. Note how the signal still rides the proper overall curve. The green curve doesn't dampen, it doesn't vary much, but it does ride that blue curve. It hasn't slowed down the overall process variable signal. The yellow line shows what happens if you put too much damping in or too much filtering. Note how the yellow line is very smooth, which sometimes operators love, but the controller doesn't know where the real level is because this dampened signal is actually way behind what's really going on inside the vessel. So that's a real safety issue, and it's also a causes all kinds of challenges with process control. If you've ever entered too much damping in a transmitter, you will instantly know because A lot of times your loop tuning goes out the window and the process runs really, really bad until somebody hopefully comes in and figures out what happened. And they tell you don't do that again. Okay, so the graph below here shows what would actually happen if you put too much damping, which 30 seconds is almost for sure going to be way too much damping, on a level safety transmitter. Um, if you'll notice that basically the blue line represents the actual fluctuations of level, right? As the vessel tilts back and forth, the vessel sloshes to one side, sloshes to the other, and that causes real level changes on one side of the vessel and the other. You can't just take the average because your gas below by, or depending where the ins and outs of that vessel are, you can still get all the bad things that can happen that we have the high and low safety limits for, whether it's liquid going to a compressor or gas blow by going to a vessel that can't handle that fast of a change, all kinds of things. So basically, this yellow line, the overfiltered signal, never passes the high and low safety limits. So the operators don't get any alarms, they don't get any trips, all is well, they think. But in reality, they may be just super close to having uh, the CSB do an investigation and say, how could this possibly have happened? Um, Damping is really good at smoothing out things like if you have a very turbulent surface on a level, or even sometimes they'll use them for platforms or ships to measure the wave height. They can filter out kind of the small waves, etc. Or in a tank, you can filter out the waves, but that's the average. We're talking about something here where the actual vessel is tilting back and forth and the real level's fluctuating. That's the real level. You don't want to fluctuate. You don't want to filter that out. That we need to know what's going on there. So if you're in the instrumentation field, engineer, technician, you always got to be thinking about what's the real level doing, and what is the purpose of what I'm adjusting here? Smooth is not the goal. Safe and reliable is the goal. Um, so that concept of just smoothing things out is just a incredibly common misconception. I don't know how, I don't know why, but that is a super common problem across a lot of industries, that people think smooth is good, and it's not. A lot of times that's the reason they're struggling so badly. We'll talk more about that later. Okay, so as an instrument professional, technician, engineer, you really have to understand a lot of these concepts well enough, not only that you don't make the mistake, but you can competently go and explain why someone should not do the plan they're wanting to take, or to convince others not to make these mistakes. Operate A lot of operations folks have it in their heads that adjusting damping is a cure-all. I don't know where that comes from, but it is prevalent through many different industries. So your instrument folks have to have the knowledge to be able to understand it well enough and explain it to prevent that scenario that I just described from happening. Um, Furthermore, damping adjustments need to be tracked just like your other critical data configuration info. If you're changing the range of a transmitter, obviously you're changing stuff that needs to be tracked. Management of change steps in, MOC, etc., or your local control system change policies, whatever it is, but it's every bit as important as a bypass or an override, as a configuration change. It can literally defeat all of your safeties. So you need to treat it that way. You need to record that data. You need to know what the damping is in every transmitter, especially on your safety ones at least. And even for process control, you got to know those so you can know what it was when the plant ran well, so you can look at it and say, did this change? Okay, so option B is also wrong. The damping shouldn't be used to mask, hide, or delay problems caused by sensors or transmitters. You need to fix the transmitter, or redesign it, re-engineer it, something, add different logic, etc. Damping slows the response and basically hides it from the controller's that need accurate and timely information to control the process and or to maintain process safety. Slowing down the signal out of the transmitter doesn't make the problem go away. It only hides it from the thing that is supposed to keep you safe and control it. So option B, definitely not the case. Okay, so option C is also incorrect. That's just a fluffy answer that's just, to give somebody a guess. Uh, there's really no situation where very few situations you're going to adjust damping to 30 seconds. That's a very slow damping, and we'll explain kind of why that is later. The process should always be, or I should say, your damping should always be a fraction of the process time. So basically, if that process is about 5 to 10 times slower than damping, that means we're looking at maybe a 5 minute single process cycle time where this might be warranted to set it at 30 seconds, and only if we have noise that's such that it's a very slow acting noise where we need that. Damping, you're just trying to remove the noise. So if the noise is fast, you don't need 30 seconds to remove it. You just need whatever you need to get rid of the noise. That's its job. So as I previously said, there's very few scenarios where we'll set damping at 30 seconds in a field transmitter. Uh, Contrary to common misconceptions, damping is not like a fixed delay. It doesn't just make it wait 30 seconds or something like that. It's actually it's an adjusting thing. It operates much like a capacitor charge or discharge. It's a filter. Um, and what that time constant is, or the damping setting, when you set it at 1 second, let's say, time constant, that's the amount of time it takes it to change by 63% of the change. Well, what's crazy about this is, well, that gets you to 63%, but in the next time constant, it's only going to change by 63% of the remaining change. So it takes quite a bit of time for this thing to reach the upper levels. You won't even be within 5% until after a few time constants. So if you had a 5 second time constant, you're talking 15 seconds before you're within 5%. And so you can see where this delay can start to really wreak havoc with process controls and with process safety, because the level jumped up immediately, maybe in theory, but you don't know about it for maybe 15 seconds. You don't get the trip or something. So, and in calibrations, this is also an issue. I see this a very common problem in calibrations. People misunderstand what this does, or they don't even look. They're doing a calibration and they don't even look to see what the damping is. So they're watching their meter, it's fluctuating around, and they go, oh, I don't know, I've waited a little while, so it doesn't look like it's right. So they mark it, and then they start misadjusting it, or miscalibrating it, because they're using the same approach of not factoring in damping when they simulate the signal and then start tweaking stuff. They do assessments, and a huge majority of the technicians I would assess, instrument technicians, qualified instrument techs, been doing this for a decade or more, did that. It's a very, very common mistake. People just don't understand damping, and our mentors, if they're lucky enough to have mentors are not talking about this stuff like they should be. These are things techs need to understand, these kind of conceptual things. So. Okay, so the only situation that I personally have worked on where a 30-second kind of time frame of damping was justifiable was in a chemical reaction measurements. In my case, it was and it's a couple times, but pH and ORP at a wastewater treatment plant, where the reaction cycle times were like 18 to 24 hours. And there was some slow mixing of the the fluids that caused some very slow noise. So we did end up needing pretty slow damping. But again, we were dealing with an 18-hour cycle time for a single cycle up and down. Um, in general, the way that I tell people to do this, you do a bump test, as I kind of described. You put the plant in manual. You have to do everything to set that up, and you adjust it by however much the operator says is safe. Maybe it's 50 to 51%, maybe it's 40 to 60, whatever it is. And you're going to do this up and down and all the typical conditions and so forth. But what you're going to do is you're going to plot a trend, and you're going to look at the actual uh, uh, noise with no damping, and that'll look like this red line. So you'll see it's responding quickly, but you'll see all this noise. I call it the grass. Uh, you start adding a small amount of damping in the transmitter, much slower than this time. If this rise takes 1 minute, you probably want to start with like a half a second or something like that. Start with half a second, and then gradually maybe double that until you start to notice a change. And you will pretty quickly. So yeah, I probably wouldn't even start with half a second really there. I'd probably start a quarter second, see how that responds, might go to a half a second. From there, you can kind of gauge it based on the response. Once you get something about like this green line, you're starting to filter that noise out. Well, let's say that happens at 2 seconds. Well, if you go to 4 seconds, you might start notice that the graph is delaying, like that previous, like the yellow line, where it's much slower, and it's actually kind of doing this response. You don't want that. That's too much damping. So you're finding that balance, and the way that I always phrase it is you're mowing the grass, you're not excavating the hill. So you do these bumps up and down, and you observe that, and you play with that damping until you get it where you get rid of the noise, but you don't slow the process down. So this question was a little bit vague and open-ended in order to spur discussion and get people thinking, and hopefully bring attention to this issue. It's a big deal in the instrumentation world. It's a big problem. Um, it's a super common mistake. It's kind of easy to make because there is a lot of theory to this. It will eventually kill people. Some of the most high risk near misses that I've observed were caused by this. A lot of times they get caught. A sharp tech comes along and notices they're in a calibration something. They pick up on something. They're getting these deviation alarms during transients or other things, and they say, "Whoa, what's going on?" They look in, but they're only going to do that if they understand these concepts. If you don't have some gurus around or some people that have been highly trained in this kind of, the theory and the concepts, no one's going to pick it up. And I've seen these things, I've seen scenarios where, you know, 60 seconds of damping set in a level safety transmitter for an unknown amount of time. No one knows how long it was there, possibly years. Uh, that's a scary thing to think about on a level safety transmitter. That's your only protection. There's no PSV. There's no other safeties that you're counting on that to protect you. Luckily, they didn't need it. Um, Additionally, very few managers understand much at all of what instrumentation and controls professionals do. Uh, so the work is often kind of neglected. It's treated as kind of black box or mystic voodoo or whatever. Uh, and then you also get the uninformed persons or the barely informed managers who are maybe a genius, but they simply assume that because they're a genius, they can make these decisions based on the word damping or time constant or whatever. And they don't know what it does. They don't know how it's going to respond. And so, they're like, well, yeah, let's do this. You really, the quote that I always think of is they don't know what they don't know. If you read CSB reports, that's a prevailing theme. Every time there's one of these investigations, somebody didn't know what they didn't know, and somebody died for it. Um, the other misconceptions are smooth equals good control. A lot of operations persons have that in their head, and it is absolutely not the case. There's a lot of times you have to balance out smooth with fast, or else you're going to have cascading events and trips and other problems. And sometimes they think that preventing alarms or trips means you're safe. Well, you can adjust the damping so that those KPIs on that scorecard for your process is great, looks great. You're never getting alarms. But when you do get that alarm, it'll be a different kind of alarm. It'll be a gas alarm. It'll be a fire alarm. It'll be something like that because You pumped a bunch of liquid into a scrubber, overflowed it, and now liquid went to a compressor and it separated and blades went everywhere, and now you got serious problems. Uh, Again, instrument professionals have to know enough to be able to go talk to someone and convince them why some of these misconceptions aren't the solution to certain problems. Couple of notes. Getting the signal damping right should be one of the very first things you do in any controls efforts. Making sure your inputs are actually working, the noise, you've mitigated the noise issues, you minimize that noise either in the transmitter or in the controller. A lot of places like to do that in the controller, but you get rid of the noise, make sure that's right. You also go make sure that your valves, positioners, etc., are working right. But that's another blog. And the other note is that, again, improper damping settings can be a humongous safety risk. It should be thought of as bypassing an override. It should be treated like that. Setting damping is not a simple thing. You almost want anyone who's not very informed on how this works. I would rather them just be afraid of damping and just not mess with it and say, I don't know, I could kill people by touching that, because that is absolutely the case. If you don't understand it, don't touch it. Um, Instrument and signal damping, it's one of the biggest problems I see in the field, one of many, that's misunderstood. It doesn't seem to get enough attention in the textbooks and in blogs and other things, for the scale of how critical it could be, um, and for how often it happens. We do cover that in our instrumentation and controls courses, for that reason. Um, so I hope that's useful information. I hope you can use that in a positive way. Please, share your thoughts. If there's anything I missed on here or could have explained better, please let us know. And we hope you can operate safely and reliably. Thank you.